Welcome back to the Get Willy Lectures is computer um, lecture series. But I am Jack Handler and I have come back from the leave or vacation. Now I am teaching you, giving you the physics lecture. So in the series we have talked about the SHM and some terms related to SHM. In the previous lecture we saw the relationship between phase difference, part difference and time difference. Let's recall again this. The part difference is given by 2 pi by lambda into part difference. The phase difference equals to 2 pi by lambda into part difference. Again, the second formula is phase difference equals to 2 pi by t into time difference. A part difference of lambda corresponds to a phase difference of 2 pi radian. To calculate phase difference between two waves, the equation of both waves must be in sine form in cosine form. And you are enjoying this beautiful sights of Indian village. And this village is near about a town known as Susant, which lie on district of Sitamarhi. And I think you enjoying the scenery of Indian village. Now let's come to the topic. Again, recall the concept of displacement wave and pressure wave. A longitudinal wave in a fluid like liquid or gas can be described either in terms of the longitudinal displacement suffered by the particles of the medium called displacement wave, or in terms of the excess pressure generated in terms of the excess pressure generated due to the compression and rarefaction called pressure wave. And equation of displacement wave S equals to Sm into sine omega t minus k, and equation of pressure wave equals to Pm into cos omega t minus k, where Pm equals to pressure amplitude. Since pressure wave is 90 degree out of the phase with respect to the displacement wave, therefore displacement is minimum when pressure is maximum, or vice versa. Now let's recall our God, Jai Bajrangbali, Jai Hanuman, Jai Shiv Shankar, Om Namah Shivaya. Please, because my friend Get Willy and Get Handler is now in their home country, I remember both of my friend, and generally I take their name. In place of my name, I take their name in my lectures. But I am Jack Handler, who teaches you physics in FFVMD Inc. Our YouTube channel FFVMD. And now I also want to get back to my country with a hike of 1000 times in my salary. And I think Bajrangbali helped me in this. So I like Bajrangbali, I pray Bajrangbali, Jai Hanumanji, Jai Bajrangbali. Now let's come to the topic. Now speed of transverse wave. The speed of a transverse wave on a stage string is given by V equals to under root T by mu, where capital T is the tension in the string, mu is the mass per unit length of the string called linear mass density. And the speed of transverse wave in a solid is given by V equals to under root eta by rho, where eta represents modulus of rigidity, and rho is the density of a solid. The devotee of Ram is Bajrangbali, so I pray Bajrangbali to help me. Now I want to get back to my own country like my friend Get Handler and Get Willie. So please Bajrangbali help me in going back to my country. Please Bajrangbali, Jai Bajrangbali. Now come to the point. The speed of longitudinal wave. The speed of a longitudinal wave in a medium is given by V equals to under root Kp by rho, where Kp is the modulus of elasticity and rho is the density of the medium. And the speed of a longitudinal wave in solid bar is given by V equals to under root Y by rho, where Y is the Young's modulus and rho is the density of material of the bar. Again, the speed of a longitudinal wave in a fluid is given by V equals to under root B by rho, where B is the Buck modulus and rho is the density of a fluid. Now let's talk about the ultrasonic and infrasonic waves. Ultrasonic waves. The human ear can hear the sound waves between 20 Hz to 20 kHz, and this range is called audible range of sound wave. And the sound waves having frequencies above the audible range are called ultrasonic waves, and the sound waves which have frequency less than the audible range are called infrasonic waves. So I think you are enjoying my lectures series. Now let's talk about the speed of sound. The speed of sound in a medium is given by V equals to under root E by rho, where E is the modulus of elasticity and rho is the density of the medium. Now a speed of sound in water is more than the speed of sound in air. Thus water is rarer medium for sound waves. When a beam of sound travels from air to water, it bends away from the normal, since water is a rarer medium for sound waves. Again, a speed of light in water is less than the speed of light in air. Thus, water is a denser medium for light waves. When a beam of light travels from air to water, it bends toward the normal since water is a denser medium for light waves as discussed. Now let's talk about the Newton's formula for sound. The Newtons assumed that propagation of sound wave in gas is an isothermal process. Therefore, according to Newton, a speed of sound in gas is given by V equals to P by rho, under root P by rho, where P is the pressure of the gas and rho is the density of gas. According to the Newton's formula, the speed of sound in air at STP is 280 meters per second. But the experimental value of speed of sound in air at STP is 332 meters per second. So now Newton's could not explain this large difference. Now Newton's formula was corrected by Laplace. So let's talk about Laplace correction. Laplace assumed that propagation of sound waves in a gas is an adiabatic process. Therefore, according to Laplace, a speed of sound in gas is given by V equals to under root gamma into P by rho. And according to Laplace correction, the speed of sound in air at STP is 331.3 meters per second, and this value agrees fairly well with the experimental value of the speed of sound in air at STP. Now factor affecting speed of sound. Let's talk some factor which affect the speed of sound. Factor affecting a speed of sound in a gaseous medium are as follows. The effect of temperature. A speed of sound in a gas is directly proportional to the square root of its absolute temperature. That is V proportional to under root T. A speed of sound in a gas at T degrees Celsius is given by Vt equals to V naught into in bracket 1 plus T by 546, where V naught is the speed of sound in gas at 0 degrees Celsius. Now for air, V naught is 332 meters per second. Hence, Vt equals to V naught plus 0.61 into T meter per second. The speed of sound in air increases by the factor 0.61 meter per second for every 1 degree Celsius rise in temperature. Let's know effect of pressure. The speed of sound in a gas is given by V equals to under root gamma into P by rho, or equals to under root gamma into RT by M, where RT and M all are capital. So a speed of sound in gas is independent of the pressure of the gas, provided temperature remains constant. Effect of humidity. With increase in humidity density of air decreases. Hence, velocity of sound V equals to under root gamma p by rho. Therefore, with rise in humidity, the speed of sound increases. The speed of sound in moist air is more than the speed of sound in dry air, since the density of moist air is less than that of dry air. Now, effect of wind on the velocity of sound. If the wind is blowing, the speed of sound changes. The speed of sound is increased if the wind is flowing in the direction of the propagation of sound wave. But if the wind is blowing opposite to the direction of propagation, the speed of sound is decreased. Now let's talk about the reflection of waves. The reflection of waves at boundary or interface between two media occurs as follows. A traveling wave at a rigid boundary or a closed end is reflected with a phase reversal of pi, but the reflection at an open boundary takes place without any phase change. Let the incident wave be represented by yi equals to a sine omega t minus kx. Now for reflection at rigid boundary, the reflected wave is represented by yi equals to yr equals to a sine omega t plus kx plus pi equals to minus a into sine omega t plus kx. So for reflection at an open boundary, the reflected wave is represented by yr equals to a sine omega t plus kx. Next point, an echo can be cited as an example of reflection of sound from a distant object, such as hill or cliff. If there is sound reflector at a distance d from the source, the time interval between original sound and its echo at the site of source will be t equals to d by v plus d by v equals to 2d by v. Now, as persistence of air is 1 by 10 seconds, echo of a sharp or momentary sound such as clap will be heard if t is greater than 1 by 10, or 2d by v is greater than 1 by 10, or d is greater than v by 20. If a person standing between two parallel hills fires a gun and hears the first echo after t1 second, the second echo after t2 second, and v is the velocity of sound, then the distance between the two hills is given by s1 plus s2, vt1 by 2 plus vt2 by 2, that is in bracket v into t1 plus t2 by 2. Now let's talk principle of superposition. Principle of superposition. It states that when two or more waves travel in a medium in such a way that each wave represents its separate motion individually, then the resultant displacement of a particle of medium at any time is equal to the vector sum of the individual displacement. That is, if y1, y2, y3, yn are the displacements at a point due to the n waves, then the resultant displacement at that point is given by y equals to y1 plus y2 plus y3 plus yn. The superposition of waves give rise to the following phenomena like interference, stationary waves, and beats. Interference of waves. When two waves of same frequency and wavelength having constant phase difference traveling with same speed in the same direction superpose on each other, they give rise to an effect called interference of waves. Now, condition for constructive interference. Condition for constructive interference, phase difference equals to 2 into n pi, where n equal to 0, 1, 2, 3, dash dash dash, and path difference equals to lambda by 2 pi into phase difference equals to n lambda, where n equal to 0, 1, 2. Condition for destructive interference. Condition for destructive interference, phase difference equals to 2n plus 1 into pi, where n equal to 0, 1, 2, 3, dash dash dash, and path difference equals to lambda by 2 pi into phase difference equals to n plus 1 by 2 into lambda, where n equal to 0, 1, 2, dash dash dash. The phenomenon of interference is based on conservation of energy. Now, a stationary wave. When two waves of same frequency, wavelength, and amplitude travel in opposite direction at the same speed, their superposition gives rise to a new types of waves called stationary waves or standing waves. Energy does not propagate in this type of wave, hence it is named as a stationary wave. And stationary waves are of two types: longitudinal stationary waves and transverse stationary waves. Let's talk longitudinal stationary waves. It is produced in organ pipe and resonance tube. And transverse stationary waves, it is produced in a stretched string and sonometer. Equation of a stationary wave is given by y equals to 2 into a cap a into cos kx into sin omega t. Stationary waves are characterized by nodes and antinodes. Nodes are the points for which the amplitude is minimum, whereas antinodes are the points for which the amplitude is maximum. In a stationary wave, nodes and antinodes are formed alternatively, and distance between them is lambda by 4. At antinode, displacement and velocity is maximum, and at node, displacement and velocity is 0. The distance between two consecutive nodes or antinodes is lambda by 2, and distance between a node and a adjoining antinode is lambda by 4. Now let's talk about the vibration in a stretched string of length L fixed at both ends. The speed of transverse waves in a stretched string is given by V equals to under root T by mu, where T is the tension of the string, mu is the mass per unit length of the string. The fundamental mode or first mode is written as lambda 1 equals to 2L, where L is the length of a string. Hence fundamental frequency nu1 equals to v by lambda 1 equals to v by 2l equals to 1 by 2l into under root t by mu. This frequency is called first harmonics. Second mode L lambda 2 equals to L. So frequency nu2 equals to v by lambda 2 equals to v by L or equals to 2 nu1. This frequency is called second harmonic or first overtone. Next third mode lambda 3 equals to 2L by 3. Hence frequency nu3 equals to v by lambda 3 equals to 3v by 2L equals to 3 nu1. This frequency is called third harmonic or second overtone. So for nth mode lambda n equals to 2L by n. Hence frequency of nth mode will be nu n equals to v by lambda n equals to n into v by 2L equals to n v nu1 equals to n by 2L into under root t by mu, where n equals to 1, 2, 3 dash dash dash. This frequency is called nth harmonic or n minus 1th overtone. In general, nu p equals to p by 2L into under root t by mu, where p number of loops. Now laws of vibrating stretch string. The fundamental frequency of a stretch string is given by nu equals to 1 by 2L into under root t by mu. So law of length nu proportional to 1 by L when t and mu are constant. Law of tension nu proportional to under root t when L and mu are constant, and law of mass nu proportional to 1 by under root mu when L and T are constant. Note, if rho is the density of the material of the string and d is the diameter of the string, then mass per unit length mu equals to pi into d square into rho by 4. Hence nu equals to 1 by 2L into under root 4 into t by pi into d square into rho equals to 1 by L into d under root t by pi into rho. Now laws of vibration of stretched strings can be verified experimentally by using a sonometer. With this, I would like to end this lecture here. Jai Bajrang Bali, Jai Hanumanji, Om Namah Shivaya, Jai Hanumanji.